Hello community, so great that you are back. Today we talk about 3 insane test time training ideas because have a look. Is it possible that we have a 7 billion model here that beats DeepSeek R1 and OpenAI O1? Yes, absolutely, with test time scaling done the intelligent way. And is it possible that we have a 1 billion LLM, a little tiny one? Does it surpass here a 405 billion llama model? Well, if we apply 1 billion with an intelligent TTS, yes, it will beat here a performance test, a single performance test against a 405B. So we are talking about some amazing enhancement here for the deep reasoning capabilities and the computational efficiencies of our LLMs that go simple beyond scaling the model parameters. So what we're gonna have a look, we have a look at TTS, and then examining 2 specific cases of TTS, we will build here finally a new transformer model. So TTS will lead us to a new transformer. 3 new research papers. Let's go for it. So if we open up this video, you know what we know in the old times. No, we have our model pre-trained, supervised, fine-tuned, DPU aligned, and the only way we could choose was simply scaling here the model parameters. Go with a 1 billion model or 405 billion llama model, and this is all we had, and we saw the world is beautiful. But now we explore test time scaling as a real paradigm shift. Focusing here on the strategically allocated computational resources during now the inference phase to really augment the inherent reasoning abilities of a pre-trained and fine-tuned LLM. So, test time scaling is happening now during the inference run. And the question is, how can we manipulate the inference process to have a superior performance here? And what are the optimal strategies for allocating and managing here the inference time compute in the best way, so that a 1 billion model, a tiny small language model, will beat a 405 billion llama model. Now you know, it is easy. We have a query, then we have here a pre-trained model, and then test time scaling, we can get some different answers. And now the idea is we build a solution space and we say, hey, let's think about this in a mathematical way, that this is a mathematical space where all the possible solutions to this specific query of mine, they live here in this box. And this is the solution space. And in some corners, they are highly complex solution. And in some corners, they are empty. In some corners, oh yeah, you get the real hint that you need to solve here the puzzle. To search here the complete solution space, you can either improve your search time, say, hey, take 2 minute time in the inference run, no? Or we improve the search algorithm, and there are the options we're gonna explore today. So let's come here to the spark of our genius that we have today. And we will know, and you know this as a subscriber of my channel, that we work here with process rewards model to navigate here the search space in order to find here the potentially best solution to this very special query of mine where a deep reasoning needs to be. And you know what is the simplest of the search space solution? No? The best of n sampling. Simply sampling here n outputs here in parallel from a base language model and selecting one that scores the highest per a learned verifier, or be more specific, a reward model. So we can have maybe another LLM, a more intelligent LLM, and tells me, hey, A3 is the best solution. Continue with A3. If you want to know the origin, and I sit down here, the origin of LLM, to my knowledge, is here either by OpenAI, or end of May 2023, where they looked here at the process supervision, which provides feedback for each intermediate reasoning step. Can you imagine May 23 OpenAI? Or, and I'm looking here at the version 3, so this is from February 2024, but also in 2023, we had here DeepSeek AI together with Tsinghua University, the University of Hong Kong, and Ohio State University. They were also here assigning here reward scores to each step of a mathematical problem solution. So, for my knowledge, if you really want to see here the origin, those are the 2 papers you should look at. But now look at this process reward model, what they do. They simply evaluate the intermediate reasoning steps, creating here a feedback loop that guides here our TTS strategies. And the alignment now between, on the one hand, the policy model, what do we have? This is an LLM that outputs here something, and the process reward model, this is also an LLM, the PRM training data. This alignment here is critically, it impacts here the reward validity and the search efficiency. So, note the policy model output and the PRM training data, they better are really connected, they are coherent, and you trained your process reward model on those data. Just a little detail, we have on-policy PRMs and off-policy PRMs. Simple. On-policy PRMs are trained on the policy model's own outputs, and they provide an accurate step-level reward, but incur training overhead. And with off-policy PRMs, you introduce here, of course, a distribution shift because you're working here with different LLMs that have been trained on a different training data distribution, and therefore you do have a distributional shift. So maybe your PRM was trained on mathematics and my policy model is in theoretical physics, so I will have a distribution shift also between mathematics and theoretical physics. It is okay. You can see this very clearly. Take simply a Mistral-based PRM, and a Mistral-based PRM assigns 83% high rewards to incorrect short answers compared to a properly aligned DeepSeek PRM. Nothing against Mistral, but a real professional model, there are still something where you can gain significant performance. Let's come to the first paper of today. Can a 1 billion LLM surpass a 405 billion LLM? Yes, of course, if you do the optimal compute test time scaling. Shanghai AI Laboratory, Tsinghua University, Harbin, and booped. Isn't this beautiful? You know what? We have the complete code for this. There is a GitHub and everything is there. Have a deep dive. Enjoy this. And you know what? The idea was simpler. This is just a week ago, February 10th, 2025. And they told us, hey, current studies do not systematically analyze how the policy models, how the process reward model, and the inherent problem difficulty, so that what I call the complexity of a mathematical problem, influence here our TTS algorithms. And they say this lack of analysis limits our understanding and our practical use of TTS methodologies. And they set out to examine this in detail, and we will have a very short look. But please, and this is exactly where I took my example for, imagine you have your DeepSeek R1 and your beloved OpenAI O1, and you can have a 7 billion TTS model that beats both of them. In logic, in mathematical reasoning. I'm loving it. Do you know what this means? This means that a 7B model is better than a 671 billion free trainable parameter DeepSeek R1. The times are simply amazing. And this is done on Math 500 benchmark. So let's have a look. Let's just understand what they are doing here. And you're not going to believe it. It's going to be a mathematical optimization problem. Like almost everything else, you know, there's nothing that you say, yeah, with common sense, I can imagine, I just try out, forget it. It's pure mathematical optimization theory. So let's state the problem formulation according to the authors here is, let's take this in detail. So we formulate the reasoning problem as a Markov decision process. Beautiful. So we define here a specific tuple where we have here the state space, we have the action space, and we have a transition function. Plus, we have here with R our reward function and a specific discount factor. And they say, now, give me a prompt X. So this is my query X. The policy with the parameters theta generates here an initial action, so the very first alpha or A1, where this is an initial state. The policy model now receives a specific reward that depends on S1 and A1. And then we have a state transition to the state S2, where this notes here the concatenation of the two strings. And I'll show you this in a bit detail a little bit later on. And this process simply continues till the episode terminates. And this is it. So, couldn't be easier. You see, this is the interplay of our models, of our LLMs. Policy, state space, action space, reward function. We have an initial state, S1. Then we have an action by the LLM. A. Then we have a transition from a particular state a S1 to a state S t plus 1. And we have a specific reward from a reward model is given that simply judges here the beneficial of this action if we want to achieve a certain goal. Now, in the classical theory, and this is now here a paper I'm going to show you in a minute. This will be our second paper of today. Just remember Snell. And now they say, hey, you know, classically, the compute, the optimal test time scaling, what we do, we follow here Snell from 2024. Because it proposes here test time compute optimal scaling strategy, which selects hyperparameter corresponding to a given test time strategy to maximize the performance benefits on a specific, very specific prompt, on your prompt. So given a prompt x, let a target of theta and an x represent here the output distribution over x produced by the policy model with the parameters theta and a compute budget of n. We have here now theta star, and this represents now the test time compute optimal scaling strategy for the problem x with the compute budget n. And you see, it is simple a mathematical optimization problem. It is so beautiful. It is pure mathematics. And now the authors come and say, hey, wait a minute, we will now optimize this, no? And the authors now say, hey, based on these findings, we propose now that the rewards should be integrated into the compute optimal TTS strategy. And again, the reward function is R, and they have now a new theta star. And they say our reward aware, this is the new part, the reward aware compute optimal TTS strategy is now formulated as this. Again, everything more or less the same, just adjusted now by the specific reward function that you choose and the reward model that you choose for your particular topic. Isn't this beautiful? And they say, hey, this reward-aware strategy ensures that the compute optimal scaling adapts to the policy model, to your specific prompt, to the reward function, leading here in total to a general framework for practical TTS, test time scaling. And with this mathematical optimization, we have now that a 1 billion Llama 3.2 model achieves parity in the performance on the mathematical 500 benchmark with a Llama 3.1 405B. Isn't this impossible? I thought this would never happen. I was sure that a 1 billion model, how can this little nothing have here the compute performance here in mathematical logic like a Llama 405B, and now, mid of February 2025, we achieved it. But it is not that some people say, yeah, just give it more time. No way. It is a mathematical optimization problem that is not trivial, because you compute now here the candidate solution under the compute optimal TTS. Yes, you generate 30 times more candidate solutions here by our little 1B model. But you don't just say, hey, do more or do the same again. No, you have a compute optimal strategy that you have to optimize. And this is now this beautiful new compute optimal test time scaling strategy for your particular query, for your particular model. Isn't this beautiful? Now, I know that there are more advanced PRM, like we're going to have a look at, and I already showed you some of them. You remember the Q-value ranking I showed you in my video about, 4 or 5 days back? You can go also with entropy regularization. There are so many more advanced PRM models, but we go here with a compute efficient model. So, again, if you are completely new to TTS, never mind, it is easy. Listen. What are the main elements? 2. We have our policy model, we call it PM. This is a specific LLM. If you think about it, this is the reasoner. This model is doing here the reasoning step. This is the problem solver to my query, to my problem that I give to the AI system. So the policy model is here the core LLM responsible for generating solution to the given prompt or task. It is the primary reasoner or problem solver in the system. And this embodies now a specific reasoning strategy, whether it's standard forward inference or it incorporates here an internal TTS mechanism like recurrent depth we're going to talk at the second half of my video. And normally we have here the Llama 3 family or the Q2.5 family. And then we have here the process reward model. Please note, this is not the outcome reward model from 2024, where we said, yeah, we just wait here till here the complete Monte Carlo tree search finishes. No, we have now a dense process reward model. And this is our verifier. This is our second brain. This is here the external coach that gives you here feedback on every step of your logical deductions. This is the evaluator. So this PRM is an auxiliary LLM responsible for evaluating the quality of the reasoning process exhibited by the policy model. A verifier, a critique, a reward function within the TTS system. But they must be coherent. They must be trained on the same domain knowledge. They must be trained to do more or less here the same task. Otherwise, yeah, if this is on a different domain, there's not a lot of value in the PRM. So careful, PRMs are sensitive topics. PRMs are trained particularly to evaluate individual steps within the solution trajectory generated by the policy model. Yeah, you have a scalar reward signal here for each single stepwise step, providing a dense reward signal for the TTS algorithm. And the PRM scores are used to guide now the search-based TTS methodology, and we already talked about best of n, we will talk about beam search in a second, in now selecting the most promising solution path and ranking here the candidate answers. Isn't this beautiful? In one of my last videos, I show you here the PRM training based on the Monte Carlo rollouts, but you don't need to go a little bit more advanced. You can go with a simple QN 2.5 mathematic PRM. Where do you find it? On Hugging Face. Here we have it, QN 2.5 Math PRM 72B. Here you have, in addition here to the mathematical outcome reward model, now a process reward model. So you can be quite sure that if you go with a QN 2.5 here as your policy model, if you take this might really have a comparable dataset training coherence. Isn't this beautiful? Yeah, and if you're new, you say, hey, what is the process now? Now the process is a 3-step process. Couldn't be easier. We have the policy model, our LLM generates the candidates. So the policy model, given now my specific prompt, generates a set of candidate solution or solution steps in a search-based methodology. We search here the complete space of all the possible solution, given that we have the idea that our solution is in this space. And for each solution step that we take here, the policy model generates this step. We have now here a search step. This is evaluated by the process reward model. This process reward model evaluates now everything. Acts as a verifier, evaluating the quality of each candidate solution of each step, assigning here the famous reward scores. And then, and this is the final part, the TTS algorithm that we use, beam search, best of n or whatever, a TTS algorithm uses now the PRM scores to guide here the selection process, the reasoning process, choosing now the most promising candidate to explore further, either in the search or in the refinement, in the self-reflection, or selecting already the best final answer in the best of n scenario, if we have a TTS algorithm of best of n. So you see, it's an easy interplay. You have two LLMs, of course it could be the same, it could be real specialized models that you train for this particular task. It's all up to you how advanced you go with those models. But in general, by leveraging here the PRM's guidance, the TTS process effectively refines here the polyphony model output distribution, leading to improved performance compared here to the standard inference of our non-TTS models. And you see, with this optimization, that we choose the right policy model, the right PRM model, the perfect TTS algorithm, and it is the interplay of those three elements that we can optimize and get a performance that is simply insane if you only know a 1 billion to a 405 billion parameter model. So what we achieved? We even had a look at a reward-aware compute-optimal TTS strategy. So of this paper, February 10, this reward integration is so beautiful because finally we integrate into optimization the reward model. But you know what? Looking at this, I say, hey, maybe I need a fresh up on what exactly is the definition of a compute optimal scaling strategy in this particular case. No? So this is now the second paper. Remember Snell? This is now a paper from Snell, UC Berkeley, Google DeepMind. Yes, unbelievable. You say, what? This is already from August of 2024? Yes, it's a good one. It's an old one, but it's a beautiful one. You know why? Because it answers here the formalization of compute optimal scaling strategies, and it has so many data. Let's jump into this. So let's come here to the core element. And the authors tell us, hey, we found that the efficacy of a given approach heavily correlates with the difficulty of the specific problem from the perspective of a base LLM capabilities. So the more difficult my query, my prompt is, the more challenging it will be to find the perfect TTS optimization. And the authors tell us, hey, this motivated us to introduce the notion of a compute optimal scaling of test time computation, which prescribes here an adaptive prompt dependent strategy to improve the performance under a given test time compute budget. You say, isn't this beautiful? So test time compute budget is clear. In the worst case, it is just 2 seconds, 5 seconds, a minute, 3 minutes, 5 minutes, 10 minutes, an hour, whatever you like. And there find here, given a time budget or a computational budget, find the best adaptive prompt dependent, complexity dependent strategy for the TTS algorithm in the combination here of the policy model and the reward model. And half a year ago, we had not yet the reward model integrated, but never mind, the results are amazing. Let's look at this here. And here you have 3 options, no? The best of n, okay, then the beam search, where we selected the top n samples at each step using here the PRM. Or then even more, a look-ahead search. My goodness, this sounds complex. And you might say, hey, this is the best model. Well, you're gonna be surprised, I can tell you. Look at this. These are different PRM search methodologies. So either you go with best of n here to the full solution and say, hey, a verify tells me that this is the correct solution. Or in beam search, we don't go here the complete way to the end, but we have intermediate solution steps. So again, parallel 4, and you see, verify tells us, hey, step 2, 3, 4, 2, and 4. Look interesting. Continue with those. You see, 1 and 3, and here. 2 goes on. Yep, this is it. This is it. And yeah, so we reach here then a final destination where the verify tells us, hey, this is your solution to your specific questions. Or look ahead. Now, this is like beam search. But at each step here, you have a rollout for 3, 4, 5 steps in advance, using here the PRM value at the end of the rollout to present you the value for the current step. So there's a lot of, let's call it guessing into this, but can give you here not just a single step trajectory evaluation, but if a multi-step, you look a little bit further in the future, but the future PRM calculations are rather not as precise as you would like to be. And here we have now the data. Isn't this beautiful? So green, we have the majority, beautiful. The best of n is here in orange. And in red, we have beam search. In blue. So you see here, if we have here an increase in the generation budget, and on the y-axis, we have the test accuracy of a particular mathematical benchmark in percentage. You see red and blue are the beam search algorithm for TTS. Those seem to be here at the beginning, here the best solution. But then you see then suddenly here we have this 3-step look ahead coming up a little bit. But then if we increase again here the generation budget, we have still here the blue, we have here the beam. And now suddenly the best of n weighted methodology shows its real power. So you see, if you compare those methodology, it is not as easy that you have one best model at a particular generation budget or to generation time, but this is a real complex thing. In order to understand the dependencies now of the complexity level, they did a difficulty bin analysis. And now they only compare the beam search and against the best of n, because those are the 2 most interesting ones. Now, to make a long story short, if you look at this, and you have here increasing difficulty level to the right, and you see you have here a TTC budget of 4, and here you have a TTC budget of 256. My goodness, 256 generations. You see the performance jump again, the same mathematical test accuracy here on the y-axis. You see, yeah, we're around 80%. But if you go to a higher complexity, you see blue dominates. And blue is beam search suddenly. So if you have a medium difficulty problems, we see that beam search demonstrate here consistent improvement over the best of n. So it is not that you go here completely, you make the jump here to the final solution, but you go segment by segment and you build here a specific beam search algorithm that seems to be and provide here some good solutions. But you see even here at level 5, it completely crushes down and yeah, great. So what we achieved with this paper, if you have a deep dive and look at all the formula. At first we have a searching. You remember we had the search space, the box. Now we are searching against the dense process-aware verifier reward model, our PRM that we already looked at in detail. And having it now, we also have here a case that we can update now the model distribution over a response adaptively. You can then go the next step to have a self-reflective PRM and. There are endless possibilities, but it is so nice you have, if you want a pure search PRM, or you go here to an adaptive refinement PRM, and I'm gonna show you here a comparison in about 5 minutes time. You have seen this before, because in the video where I showed you AI agents new inference reasoning with QNet, the QLAS, we did exactly the same, no? We had here our inference, TTC reasoning is happening. We had here the final answer, and we said, okay, if you only have a final reward signal at the end of thinking, this is not as great. We used the Monte Carlo tree search methodology to build the reasoning trees. And then at each step in the reasoning trees, we will use here a process reward model to provide here some hint. At the first run, of course, it was just a Poisson distribution. A process reward model that then we can optimize, and this will help us in deciding which is the perfect way, step 1, step 8, step 12, step 15, to arrive at the correct solution. This is more or less the same, we just use different tools, Monte Carlo tree search, but you see we also used here for the search algorithm, but for the process reward model, it was more or less the same idea. So you see, we are circling here in mid-February 2025. We are here all about the same topic. We are sitting in our helicopters here, cruising here over this target area. The study had a beautiful takeaway, and I want to show you this. The test time, this one here, and the pre-training compute, so the very beginning of our LLM, are not one-to-one exchangeable. And they come to the conclusion that an easy and medium mathematical question, which are within a model's capabilities, the test time compute can easily cover up for some additional pre-training. However, now, on more challenging question, if we increase the complexity of our task, which are outside of a given base model capabilities, a 1 billion model, the pre-training is likely more effective for improving the performance. So we do run into a wall, of course, but that a 1 billion can outperform a 405 billion, I would say the wall is quite far away, but it is there. Of course, it is there. So we cannot do everything here in the TTC reasoning complexity if the pre-training has not already been at the same level of complexity before. We can go maybe a little step further in the complexity, but there are limits. Great. You know this. We started with this. And now we call both methodologies that we looked at, more the real search test time scaling and then the refinement test time scaling. Both of these models are called external TTS, test time scaling, compute scaling algorithms. And now let's come here to a fact that is simply amazing. We take this now and we say, this is great, but you know what? We bring it back into the training time. We say, hey, if this is what makes our model reason better, reason more, we have now understood the algorithms In the test time scaling to optimize the inference reasoning process, now we take this and we say, great, and we build it into the model in the first place. So we say, let's do here the third test time compute scaling. Let's build here a latent mathematical space where we can implement this optimization. Now there's something now going wrong, and you clearly see this because this is not test time scaling anymore. We are here in the training time compute. The latent space is not in the normal transformer model that we have. So we have to modify now the real transform architecture of our LLM. And the simplest way is we look here at recurrent models. We look here at DT models, deep thinking models. I'll show you this in a minute. So what we do, we add a recurrent block to the transform architecture. So we modify here the underlying architecture of everything, our transformer. And we add a recurrent block. And this is the beautiful study, February 7, 2025. And you have here, this is from Institut Tübingen, Max-Planck Institut für intelligente Systeme, Deutschland, Germany, University of Maryland, and the Lawrence Livermore National Laboratory. And they published this and they said, hey, you know what? Now, they also called it a scaling up the test time compute with latent reasoning. A recurrent depth approach. But it is not really precise because we just take the ideas and the algorithms from the test time compute optimization. We build a general recurrent depth architecture, and then we apply latent reasoning in the training time compute and in the test time compute. So let's be a little bit more specific. We build a complete new architecture for this. We build a new transformer model for this, given our insights from TTS. Embedding here the capacity for iterative computation and compute scaling directly into the language model core architecture. So we modify the transformer itself and you say, hey, finally, yes, great, let's do this. Now the authors built a very tiny 3.5 billion pre-trained parameter small language model. And now they built here this with the new recurrent block in its architecture. And they call it here LM, the language model with adept recurrence. And you might say, why? Now, depth will be really easy. Recurrence, if you're not familiar with the latest years in AI and statistics and theoretical physics and computer science, it is easy. It is easy. Recurrence simply means we have here kind of a spiral, and we spiral deeper and deeper into the reasoning. So this is, it's not a loop, this is more than a loop. This is really an improvement, going down and down and down, deeper and deeper in the reasoning process. But since this is now a recurrent block in the architecture, this block, if we do now the training, the block is here, and if we do here the test time scaling, the block is here. So this is an inherent part of the new transformer architecture. So you can't call the block here a test time scaling block. No, it is an original inherent block. It is there, full stop. So let's forget that this is an internal test time scaling element, because test time scaling is this here. This here is not test time scaling. So yeah, there's a little bit of a hiccup here with the precise marketing, but you know exactly what we are looking for. So having now this recurrent block as an inherent part in the architecture, the test time, the model can now iterate longer to use more compute and improve its performance. And I know what you're going to say, but this is not a test time algorithm. No. Let's have a look at it. Let's clarify this. We call this here, we train here a language model with a depth recurrence module, a recurrent block. So we modify the transformer in the training time compute already. So this means we need a new training algorithm, a new training process to train this kind of transformer for our deep reasoning. And then the block is there as an inherent element and we can use it then. But instead of scaling here the test time reasoning by verbalizing here in long chain of sorts, the model does something else. The model can now improve entirely by reasoning in a latent mathematical, in a pure mathematical state before any verbalization is happening. Nice, you might say, because normally our test time scaling is happening when the verbalization has been done, when the sentences have been formed. But no, we stay in this pure new mathematical compute state. And to be precise, to a level that you say, hey, you are crazy, it is not here scaling test time reasoning. Because I will show you a surprising effect at the end of this video. So one way to unlock all of this, and I thought about this for years. I'm not like my subscriber who leaves me a comment and says, hey, I thought about the same thing like you showed me that here Stanford or MIT or Harvard was doing. Now, I had the same feeling, there's an untapped potential if we just do this in a loop. Why not go loop, loop, loop and reasoning deeper and deeper and deeper? And this is exactly what they're doing. But you don't use here a transform architecture for. But you add here a recurrent unit here to our LLM. And this unit runs in a loop, which is not really correct. It's more a spiral, but never mind. So we have iteratively processing and updating its hidden state and enabling here computations to be carried on almost indefinitely. So this is the main idea. In our transform architecture, we have a recurrent block that is just thinking. It does nothing else than think. But how do we build this block and what are the elements of this block? This is the interesting thing. Yeah, if we have this block and we have test time, inference time, the model can now improve in its performance to the recurrent reasoning in the latent space. And that's it. This is an additional feature. And this is the reason why with a 3.5 billion with recurrent depth module block can now have an equal performance in a mathematical reasoning to a 50 billion model. So you see, suddenly we bring over all our insights from test time compute scaling into how to optimize the transform architecture itself. If you look, this is a mathematical space. We can analyze here the features in this mathematical space. And if you are a little bit on the mathematical side, you do this. And you see that in this space, something happening. We have some symmetries developing in the space if we do here deeper and deeper and deeper reasoning. And there are now shapes developing in this pure Latin mathematical space here, especially if you do numerical computation. And there's now a complete new theory. I mean, for me, because I'm a stupid idiot, but if you have a PhD in mathematics, you know that there are elements in the pure mathematical theory that would support this, but more about this in a later video. Great. Yeah, let's look at the model now itself. How do we build the recurrent block? Ladies and gentlemen, this is the way you do it. And I have here a screenshot to be as precise as possible. The model is primarily structured around the decoder-only transformer block, so a GPT model. These blocks are structured into 3 functional groups. Now, like in music, we have a beginning, this is called the prelude. And then we have the end of the music, this is the coda, this is the end of the music. So we have a beginning and the end, and now you're not gonna believe it, but in the middle, there's also something in the middle, and we call it a recurrent block. The prelude is simple. It embeds here the input data into this new mathematical space using here our transformer layers that you know. In the recurrent block itself, so when we have established a mathematical space, this is our central unit of computation. And we just compute and modify states to the extent I already shown you the formula. And if we have done all the calculations, we have at the end of the decoder, we unembed here our result from the latent space and then bring it back here with a prediction head here to the verbalization. That's all there is. The only special element is that this recurrent block you can have here spiral down in the reasoning. So if you want it in a real simple way, think about this. First step, the prelude is we embed data in this new mathematical space. Then we calculate the data in the latent space with the recurrent block. And at the end, we unembed, we extract the data from our artificial mathematical space, from the latent space, and convert it back into words, into sentences. That's it. Yeah, each block contains multiple layers, and each layer contains here the standard causal self-attention block using rope and here a gated MLP. Plus, we use here the classical RMS norm as our normalization function. There is nothing particular interesting to this. We have our self-attention block, we use here positional encoding, we have our MLP, we have a normalization function. Everything is as normal. But how do you get the idea that you say, hey, wait a minute, I put here a recurrent block here in our transformer. Where does this come from? And you might say, hey, wow, this just happened overnight. I'm so sorry to tell you, no, this took years to develop and hundreds of people. So the idea originated, according to my humble opinion here in the literature, on the recurrent neural networks, or what they call here the deep thinking networks. It is damn difficult to get an original paper from the time. I mean, we are talking here about 2023. Everything disappeared behind paywalls by the publishing houses. I have here only here, as you see, paper under double-blind review here for the conference paper 2024. But this is the paper by Schwarzschild et al. From 2023, talking about here the latest development in recurrent neural networks. Schwarzschild is here one of the main authors if you want to know about DT nets, about deep thinking networks. Over there, the whole theory of a recurrent block more or less originated. And I read Schwarzschild starting 2020, 2021, so this is from 2023. So you get an idea, hey, there are 5 years of research here in whatever consortium where they already prepared here the way for this. The prior work makes clear that these DT nets are capable of learning scalable algorithmic processes that can solve problems of arbitrary size when trained only on small examples. This was the fascinating idea. This was the hook that they said, hey, how is this possible that this is working? So DT nets in itself, a beautiful theory that you can have a deep dive, but gee, everything almost is behind here paywall. So if you find here some of Schwarzschild's archive, a PDF link, please put a link here in the description for the community to find it, because otherwise you see I have to go here with double-blind reviews. This recurrent design here was here kind of a minimal setup required to learn here stable iterative operators. And they give us here a beautiful example here for the recurrent design, why they took here this recurrent block as the main element of the new transformer. Think of this as a gradient descent of a function. X may be a variable of interest and y is not a data. Now the gradient descent of this function starts here from initial random state, x underscore zeros, and repeatedly applies here a simple mathematical operation, the gradient of the function, and optimizes, and it depends here on the previous state, x underscore k, and the data y. Note that we need to use y in every single step to actually optimize our function. Similarly, we repeatedly injected the data e in our setup in every step of the recurrence. So given here from the example of a gradient descent, they found out if they use this recurrent block, they have to feed the input continuously into this block, which is interesting in itself. So if you want to have a little bit of a deep dive into the recurrent block, or you have an adapter matrix here. So the recurrent block first uses an adapter matrix that takes here the concatenation of the current state S I-1 and the input embedding E. And this operation maps here the combined vector into the model hidden dimension. And this concatenation, as opposed to addition or whatever the authors tell us, we have found that this works best. And if we have this, after the adapt, the output passes through several transformer layers, and these layers are organized now in a specific sandwich format. You have the classical attention sublayer with the causal self-attention using rope here for positional encoding, Then you have your MLP, and you have here the norm for stabilization. There's nothing particular to this here at the end. You have another layer for the normalization. Beautiful. If you are not sure about rope, go to my channel, put in rope. You have 2 videos, rope positional embedding up to 100K context length and up to 1 million token. And now this recurrent block, as I told you, it is an inherent part of the transformer. So we use this now, the recurrent block, in the training phase. And then, if it is trained, this is now the beauty. In the test time scaling, we can also use another recurrent block. So let's have a look at this. So in the training phase, the integrated recurrent block is built on a transformer's computational graph. It is used to iteratively update the latent state S by combining here the input embedding E with the previous state. Beautiful. And during the training, the number of iteration, the number of spiraling down, is randomly sampled from a log normal Poisson distribution. And this variability ensures that the model learns to handle different computational depths, effectively teaching it to sync with various amount of compute deeper and deeper. And then at test time scaling at the inference run, we unroll this. The same learned recurrent block is now applied, but you can choose to run more iterations that were typically used during the training. If you add here, 20 or 25, go with 30. So this extended unrolling allows the model to allocate additional compute for deeper reasoning. Because the recurrent block is active during the training, the model becomes more robust to the changes in the number of iterations. When you scale test time compute, it behaves like a standard transformer module, but with an extended depth of thinking, of reasoning, of computation that was learned during training. So again, the training performance is one of the dominant factors. If you have a good training, you will get a good inference run. Test time scaling might be, again, not the right wording because TTS is not really what's happening here. We just use here an architecture element of a transformer where we can say, okay, go down the spiral 30 times. This is, if you want, this is a kind of scaling, okay. But yeah, so be aware we have now 3 different types of TTS. The authors showed us here for the training data, they give us everything. They make it open source. They give us the pre-training data, everything. And they are able to schedule here close to 800 billion tokens of pre-training here for the main model. You just go there here to the GitHub repo, beautiful, you have Apache 2 license, great, all the data is there, all the recipes are there, all the training routines are there. They give you the details to really beautifully write out everything that you should use for the tokenizer, the downloads, the script, the Parquet files, everything. It is beautifully documented. And they say now final model is now here the Hugging 0125. Beautiful, and of course you find it on Hugging Face. Isn't this beautiful? What I personally found interesting is not that it was trained here at 800 billion tokens, but it was trained on AMD's AI machine, the MI250X. Not the 300, the new 300, but the old under quotation mark, the old 250X. So real interesting to see that now people start here to train the new transformer models on the AMD AI machine and not just on NVIDIA GPUs. Okay, so this was quite an interesting thing to learn and to prepare this video for you. And I have to tell you, I learned quite a lot of this. So if we talk about 3 different axes of TTS, or 3 different models of TTS. So let's have a look at the simplest one, the first 2. We have, as I told you here in the box, we have a search-based TTS with our PRMs, and then we have a revision-based TTS with our PRMs. And here you see the different mechanism, role, process, and analogy. Search is simple. You just explore here multiple in parallel independent candidate solution. Revision-based, you iteratively refine here single solution through self-correction, self-refinement. Beautifully done, but you need, of course, a PRM. So the PRM here picks, if you want, the best revision model from all the revisions that are offered to you, and the PRM chooses here, this is the golden way to go. If you would like to think this about a map and an analogy here, so here with the search-based TTS with the PRMs, You explore multiple routes on a map, guided here by the expert feedback of your PRM. And revision-based, you iteratively refine here a single route, but guided constantly here, step by step, by the expert feedback of a PRM, where you revise here and you say, maybe you can come back here another step if you're not successful and find another way. It is completely up to you which of these two TTS to choose, but be careful. Now you know the PRMs for this particular task. You must choose carefully from Hugging Face. And the third axis of our, if you want, TTS, the third methodology, the induced methodology now is latent reasoning. It really dramatically improves the performance on the reasoning task, on the deep reasoning, on the complex reasoning task by expanding here the test time computation, but not by TTS algorithm itself, but because we activate the recurrent block, which is an inherent architectural element of the new transformer. Beautiful. And let's finish here this video with the original wordings here from the authors. And they say, this leads us to believe that this latent reasoning is a promising research direction to complement existing approaches for test time compute scaling. And there you have it. This is complementary to the other two methodologies I just showed you. So we really have, if you want, 3 different versions. So pure search-based, revision-based, you can have even some hybrid version of this. But then this opens up now, again, if you do the training phase right for the recurrent block, this opens up a third optimization problem for you. So you can gain additional performance for your model. But hey, this, just to tell you, this was just more or less a mathematical proof of concept. A model, the 3.5 billion parameter model they built, was just, in my simple wording, a proof of concept. It is not really established knowledge. We just started to explore this. We don't know about the problems we're going to encounter, but it seems that this methodology is real interest. This new transformer architecture has really some interesting aspects to this. But of course, the negative side is we have to start here the training phase of all these models again, but we can reduce the complexity in the pure training data. But now here the first problem, how far can we reduce the complexity? The authors argue that you can reduce the complexity in the training phase quite significantly, but I do not think so. I think there's somewhere a threshold. If you make it too simple, the model cannot simply discover how to have here an integral form or solve here some differentiation equations suddenly, if you know just plus minus. So this will be absolutely fascinating in the future. So why don't have you a look at these topics? Why don't you read these papers? And I'm sure this just happened this week, so maybe next week we will have the next paper on this. But for you to know, we have more or less 3 different axes of this test time compute scaling. 2 that are established, and the third one that is brand new transformer, new proof of concept. And my goodness, the future is absolutely interested. And if you are interested to see more of this video, hey, why not subscribe?